three dots already. Oh. خلاص يعني if anybody start recording خلاص it's now it is started recording. So let us go to our class. So this is bar angle equation, and definitely you know what is a bar angle equation. What do you think this equation would be? What is bar angle equation? B equal to, or B max, let us say, is sine delta. So this is the bar angle equation. Okay, so last class we discussed the simplified model of the synchronous machine, and we checked the stability condition where the angle shouldn't exceed 90 degrees. And we also consider the case of two machines, and also we consider the case for multi-machine. So for a given network configuration with constant voltage magnitudes of the transient internal voltage, which is E prime. Transient, we mean, as we mentioned last class, transient means prime, subtransient means double prime in our notation here in stability. So this is E prime. Internal voltage, induced voltage inside the machine, transient internal voltage of the two machines for a machine and the infinite bus. Of course, as we mentioned earlier on the infinite bus, you can consider it as huge machine. H equal to infinity, short circuit capacity equal to infinity, and we discussed this infinite bus concept. So for one machine connected to infinite bus or huge machine here, so we have internal voltage here E1 and E2, and for negligible armature resistance, this is usually the assumption, armature resistance is very small. The bar angle equation of the network is defined as BE equal to B max sine delta. Okay. Okay. So for two machines, you have voltage E1 prime and E2 prime, and the transfer reactance is X12. You can write it in terms of transfer admittance instead. So it is E1 prime times E2 prime times Y12. So X12 is called the transfer reactance, Y12 is called the transfer admittance, and E1 and E2, Y12, X12 are all magnitude values. There is no complex numbers involved here. This is power, and the power should be real number. So E1 as a magnitude, E2 as a magnitude, and also X12 as a magnitude. So this should be a real number at the end. So this X12 is a transfer reactance. And I think in 520, you covered this point, how to get the transfer reactance X12 by very systematic way, very simple system. If you have very simple configuration, you can get X12 maybe in a steady state or pre-fault, during fault, and post-fault. You can have this transfer reactance in different configuration. And for example, if we have here a generator and we have here a transformer and two transmission lines, for example, and these are connected to infinite bus. So XD prime here equal to 0.1, this is 0.2, and this is 0.4, and this is 0.4. So how much X12 in normal state, in a steady state, how much X12? Any answer? Abdulaziz Khalid, please.
0.5.
0.5, which is mean 0.1, this one, plus 0.2, plus these are in parallel, so it's 0.2. So this is 0.5. Okay? Right. If we have a fault here, if we have a three-phase fault here, can you get X12 during the fault? Ayub, Khalifa?
0.3.
0.3. You mean 0.1 plus 0.2? If this is the transfer impedance between X1 and X2, between bus 1 and bus 2, or generator 1 and generator 2, or you have something else. Now we need a transfer admittance, transfer impedance X1, 2. So 0.3 is not you know, is not right. طيب نشوف عبد العزيز. خلاص عبد العزيز already answered. عمر سلمان. عمر سلمان.
Okay, doctor.
How much X12 if we have a three-phase fault here at this bus?
0.7.
0.7. From where you get 0.7? You mentioned when this line is out.
This is shorted. Yes.
This line
is shorted.
disconnected. But this is not. But this is not during the fault, and I am talking about during the fault. Maybe to clear the fault, you isolate this line. In this case, we have another configuration, so we have another value of X12. Yes, if this line is out, but this is post fault.
Okay.
This is to clear the fault. So it becomes 0.7. But during the fault, how much the transfer impedance between 1 and 2, between generator and the infinite bus? Ayub, do you have another answer?
No.
طيب عماد سليمان؟ لا ما فيش.
Yes, maybe in parallel, 0.3 in parallel with 0.2.
With 0.2. يعني
Yes.
you have this 0.3 and 0.2 here in parallel. So you are calculating the impedance as seen from the fault points. So you have this is parallel with this. But X12, this is not X12. X12 is a transfer impedance between 1 and 2. If you say 0.3 parallel with 0.2, that means you know you are looking to the system from here. So this is the Thevenin impedance between this bus and the ground, which is 0.3 parallel to with 0.2. But this is not X12.
Okay, doctor.
Raise your hand. Raise your hand if you want to answer, just to know who's talking. Okay, Omar. What do you have?
0.2 in parallel with 0.3.
And this is what we have discussed here. And this is not the transfer impedance between 1 and 2. This is the Thevenin impedance between this bus and the ground. You have this 0.3 parallel with 0.2. So this gives you the impedance between these 2 points.
Yes.
Between the bus and the ground. This is not the transfer impedance. Definitely you cover this in 520. Abaziz.
Maybe 0. It's a
0.
short circuit.
No, it is not 0. It is not 0. طيب أيوب وائل.
Doctor, maybe it's only 0.2.
0.2. Which 0.2? This combination?
Yes, the parallel of 0.4 by 0.4, and the others are already shorted 0.
Again, this is not X12. طيب نشوف عماد سليمان.
Yes, Doctor. Maybe it is infinity because I don't think it will run the current between the X1 and 2.
You are absolutely right. X12 equal to infinity.
Okay, thank you.
Yes. Do you have another answer, Omar? Okay.
No, doctor.
Lower your hand, please. X12 equal to infinity. X12 equal to infinity. There is no power transfer between the machine and the infinite bus. There is no power. If we have a short circuit here at this bus, in this case, there is no power will go through the transmission line. There is no power transfer. And this is very simple, can be evaluated or developed here. We have here this configuration means we have here 0.3 impedance here, 0.1 plus 0.2, and you have a short circuit here, and you have here 0.2, which is the parallel 0.4 with 0.4. So with this, now what we need is this is the definition of transfer reactance. Transfer reactance means, and we need to simplify the system to have a direct connection between 1 and 2. So can we eliminate this configuration to have direct connection between 1 and 2? Direct line? Yes, we can do. Assume this is here, the impedance here equal to 0. X here equal to 0. So this is Y connection. We can convert it to delta. So what is important for us? This is X12. This one will be X20. This is a reference. So this one will be X20, which is not important for us. And this is X10 between this bus and the ground, which is not important. But this one will be X12, this impedance. So you can convert Y to delta. So this X12 in this case, during the fault equal to X1 plus X2, X1, this is between here, X1 plus X2 plus X1 x2 over x3. So this impedance equal to x1 plus x2 plus the multiplication x1, x2 over x3, the far impedance. So the far impedance equal to 0, short circuit. So this gives the x12 equal to infinity. So that means no, there is no power transfer during the fault. If the fault occurs at this bus, now if the fault occurs here, this is something else. And if the fault occurs here, مثلا at the midpoint of the line, يبقى we have here this is the fault. You have a fault here, three-phase fault. So we have here 0.2 impedance, 0.2, and this becomes 0.4, right? So when you have here a short circuit, so this impedance is connected to ground and this impedance is connected to ground. So the first step we can have to simplify this circuit is to have this generator and the transformer and this line and this impedance, which is 0.2, and this impedance, which is 0.2. So if this is the midpoint of the line, half of the line here and half of the line there. So this is 0.4. And in this case, again, we will convert this 0.4 and 0.2 and 0.3 here. So these impedances are connected Y, so we can connect them delta, and we can get delta transfer, and we can get x12. So in this case, x3 here is 0.2. It is not 0 as we have the fault at the bus. If we have the fault at the bus, then x12 equal to infinity. If it is somewhere in the line, we still have some power transfer. Yes, the power will drastically change or reduced. The power transfer is drastically reduced, but still there are some power transfer with the infinite bus from the generator. So in this case, we can have x12 is different than infinity. But for the fault here, x12 equal to infinity. All these configurations and these things, I think I urge you to go for 520 and try to go over the stability part there, where you have this calculation of x12 pre-fault, during fault, and after the fault. And we will use these concepts here. So this is x12. And y12 is just transfer admittance. Of course, for simple circuit as such, single machine infinite bus, you can do this simplification. Series, parallel combination, Y delta transformation, and so on. But for multi-machine system, this is not valid, and you have to go for Y bus system, and you have you can form the bus impedance matrix, and you convert it to bus admittance matrix, and you can get x12 or y12 by matrix notation. Okay, so so this is the power calculation, E1, E2 times y12. It can be observed from the power angle equation and the power angle curve shown here that the steady state stability limit for synchronous machine connected to an infinite bus, you have to have the operating voltage, operating angle is less than or equal 90. Okay. I received a reminder for prayer. So should we stop for 5 minutes?
Yes, Doctor.
Yes.
Right, okay. Now it is 5:45. So we will be back inshallah 5:50. Okay, let us resume our class. So as we mentioned earlier, the condition for stability is to have the rotor angle less than or equal 90 degrees. And if you still remember from the last class, we call this point as stable equilibrium point, and this point is unstable equilibrium point. Okay, so this is the bar angle equation. So the possible swing curves for the stability process are shown below. So you can have any of those curves. This is unstable performance. You can see the angle increases monotonously. This is underdamped condition. System is stable. The oscillation or the deviation of the angle is decreasing. This is critically damped. The damping coefficient equal to 1. This is overdamped. Damping coefficient is greater than 1. So you can have any one of those responses of the system. If you have a disturbance, in this case, this is the swing curves or delta versus T. The lowest solution of the swing equation. Okay, any question? So let us take this example, consider the one line diagram and the corresponding reactance diagram of the two machine system. You have generator, motor, two transformers and transmission line. So how many impedance do we have here in this configuration if we convert it to impedance diagram? How many impedance? Yes, Hussein.
5.
5. XD prime of the generator, X transformer 1, X line, X transformer 2, and the reactance of the motor. So you have X synchronous generator, X synchronous motor. Both are 0.4 per unit, XT1, XT2. Transformer reactance 0.1 per unit, transmission line 1.2 per unit. And this is the impedance diagram. This is the generator equivalent circuit. This is the motor equivalent circuit. This is the line, and these are the two transformers. Analyze whether the system is stable enough in the steady state to deliver 1.2 per unit, and the power delivered is 1.2. We need to check whether the system is stable or unstable under this power transfer, under this condition. Per unit power at the motor terminals with rated terminal voltage and 1 per unit, one power factor or unity power factor. So can we check? And we have here a power transfer equal to B12 equal to 1.2 per unit. And rated terminal voltage at the motor, and the voltage here is 1 per unit rated. VTM is 1 per unit rated voltage. And the power factor is unity. Power factor is unity means no current in phase with the voltage here. So can we analyze, can we check whether the system is stable under this condition or not? And we need to repeat A or a second line of the same size in parallel with the original. Assume that you have a transmission line here, additional transmission line. So can you reconsider the case and evaluate whether the system would be stable or not? Before starting, what do you think for part B? System will be more stable or more unstable? And assume that we have a certain case in point A. For point B, the system will, the stability will improve or will degrade. Sir?
The stability will improve.
By adding a line, the stability will improve. Why?
Because X will be decreased.
Yes, you have here, in this case, you have two transmission lines in parallel. So the equivalent reactance will be half of the line. So in this case, we have a reduction of X. And if you reduce S, if you decrease X here in the denominator, so you can transfer more power. So the stability will be improved definitely. And if you consider this is the case here, assume this is the case A. Where is case B? Up or down? Assume this is the power versus delta.
Up.
Up. So this is the second case. So if you have, this is the mechanical power. This is the initial operating point for case A. This is the operating point for case B. As you can see here, the angle of case B is lower than the angle of case A. So we are getting lower than more and more lower than 90. وبالتالي السيستم will be more stable. Okay, and 90 represents the stability limit. So if the point is here, if we have point A or point 1 and point 2, in terms of stability, point 2 is better than point 1. Then you still have a large margin to the stability limit. So in this case, if you increase one line here and you reduce the reactance, then the angle will be reduced. And in this case, you have better stability condition. So can we solve the problem here? You are given the power, you are given the terminal voltage, you are given the power factor. So can we proceed to get EG and EM, and we get the current, and we get the angle, rotor angle of EG, rotor angle of EM, and we can take, for example, VTM as our reference, one with angle 0, so we can get all these currents and EG and EM and so on. Can we do this?
Sure.
Okay. Oh, there is a point, another point here, which is C. What is the maximum power? What is the maximum power that can be delivered in part B? Okay, so what is the maximum power for part B? If this is part B, This is part P. So what is the maximum power here? Okay, this is straightforward. Right, let us start with the getting E, G, and EM. Ayub Wael, do you have a question?
Doctor, I have just a small question. We always see that X, reducing the reactance of the line by, adding one parallel line or add capacitor bank from both ends will improve the system. But what is the disadvantage of, reducing the reactance?
Disadvantage?
Yes.
لا بالعكس, there is no disadvantage of reducing reactance. يعني in terms of يعني if you reduce the reactance, يعني that means there is no voltage drop, there is no losses, and you have very strong line, very strong system. And as you mentioned, for infinite bus, internal impedance equal to 0. So this is why voltage is constant. So
But against the short circuit, it will not have drawback to reduce the reactance to some limit.
short circuit capacity.
Yes. So the short circuit current will be very high, if the reactance will limit also the short circuit during fault.
Oh yeah, but you can to limit the fault current. You can have in grounding, you can do this. And in grounding, usually for a steady state case, for the normal operation, if we have reactance equal to 0, that would be great. Let us agree on this. Okay? Do you agree with this?
Okay, yes.
Now, during the fault, can we reduce the fault current? Yes, we can reduce the fault current. There is a device which is called fault current limiter. That this device, when we have a fault, can limit the current, can insert an impedance here. And let us assume that we have an impedance here in parallel. If we have high current here, high fault current, this impedance will come in the picture. You have some electronic devices, you have a transistor or MOSFET or any electronic device that sense the current or sense the voltage. And during the fault, the voltage is very low. It can be based on the voltage or based on the current. If we have high current or low voltage, in this case, we insert this impedance in the circuit to limit the fault current. Okay? But in normal operation, this is not in the circuit at all. One other way to limit the current is to ground the neutral of the transformers here and there. At the for motor, the motor is connected Y, so you can limit the fault current. This is limiting the fault current here. This neutral impedance. طبعا in normal operation, this impedance has nothing to do with the circuit. In normal operation, balanced three-phase. So there is no current to the ground. If we have single line to ground, so we have the 0 sequence current, and the fault current in this case equal to 3 IA0, 0 sequence current. So if you have this impedance in the path of the 0 sequence current, so it will limit the fault current. So this impedance also will limit the fault current. You can have a shunt impedance here. This will be connected if the voltage is very low or the current is very high. That means we have short circuit. So this will be connected to the circuit. And in normal operation, if the impedance is 0, that would be an excellent situation. I hope I addressed your question.
Yes, thank you, Doctor.
Omar?
Yes, Doctor.
Yes.
Yeah, I just want to say that a disadvantage will be
Just
in terms of
Omar,
economic. No?
I just want to say, please open your Blackboard. There will be a quiz maybe in 2 minutes from now. So what is your question, Omar?
No, I'm saying that a disadvantage of having two lines, decreasing reactance will be in terms of economic, that it will cost more to do that. I don't know if this is correct.
Of course, if you try to increase the power transfer, one option is to install a transmission line. Another option is to put a capacitor here, series capacitor.
Yes.
And this XC will be 1/2 of X line. And this is a negative. So the total is maybe 1/2 of you can have 50% compensation. If you add this capacitor, which is 1/2 of X line, as if you installed another line here. So this is, of course, more economic, but there are a lot of challenges here also. A lot of challenges in terms of dynamics, in terms of the phenomena, which we call it subsynchronous resonance. Introducing this capacitor might excite resonance, and if this happens, subsynchronous resonance, this will damage the rotor of the synchronous generator. And it happens in real life. It happened in real life twice, in 1969 and 1970, in the same station, generation plant, and they experienced a complete damage of the rotor of the turbine and generator, and they stop things until they, formulate this issue, and they investigate the events. When it comes at the first time, there was no problem. And they installed the generation plant again, and they operate it. But again, it happens the same, same damage of the generator, and then they stop. And this was a series compensated transmission line connected to the generation plant here. So this will create a problem. You have to be careful. You have to do study before deciding how much compensation you need here. You have to carry out this subsynchronous resonance study. I think Q2 now is available. So please, you have 3 minutes. Three questions, 3 minutes. Okay, so let us continue. So this is the solution. We will consider the voltage at the motor as our reference with angle 0. It's a rated voltage, 1 per unit. And then the current equal to this. So from where you get this value? From having B equal to 1.2 per unit. So B equal to VI cosine phi. And this is the power factor, which is 1. It's given, the power factor is unity. So the voltage is 1. So the current is 1.2. And with angle 0, then unity power factor. So this is the current. So if you have the current and you have this voltage and you have these impedances are given, so in this case you can get EG. EG equal to the voltage here plus current multiplied by all these impedances. And EM equal to the voltage here minus, then the current is going down, minus the current multiplied by JXM. And then you can have EM equal to VM minus JI X motor, and you can have it as such. And E generator, you can have it also EG equal to VM plus the current multiplied by all these impedances. So you can get an EG equal to 2.38 with angle 65.2. What is the angle difference? This will indicate whether the system is stable or not. You have here, this is the EM has an angle here equal to 25.6 negative, and this is EG. You have the angle here equal to 65.2. So how much the angle between point 1 and 2 or generator and the motor, this will give you the delta 1, 2 or delta GM, which is delta G minus delta M. So you can have it equal to 90.8. So this is the rotor angle in this case. Would be the system stable? Would be the system stable or unstable?
Unstable.
Unstable. This exceeds the 90 degrees. وبالتالي يبقى unstable. Under this 1.2 per unit power transfer, the system is unstable. We are here. طبعا how much B max? What do you think? How much B max? Is it greater or lower than B1, 2?
Less than.
Less than. B max less than? Let us calculate it. B max equal to 1. Equal to what? Equal to 1 point this multiplied by 2.38 over the total impedance, which is, so this is, if you have a calculator, so you can calculate it directly here. 1.109, 2.38 over the total impedance. The total impedance, which is given here, total impedance at the 0.4 over 0.8, يبقى 1, يبقى 2.2. Total impedance is 2.2. So what do you think? This, how much it is?
1.1.
1.1. 1.1. This would be a little bit higher than 1.1. right?
It is 1.1997.
1997 يعني almost 1.2. وده واضح حتى من الانجل. It is almost 90 يعني here. So the system is unstable. طيب for point B, if we add here a transmission line in parallel, so the reactance of the equivalent here becomes 0.6. So for lines here, the reactance becomes 0.6 instead of 1.2. You divide by 2. So you have an EM is the same. And the EM is the same. The voltage of the, if you take the terminal voltage of the motor as your reference, again, you have this EM is the same. But the effect you will come here for EG. Then this reactance now is different. XL here is instead of 1.2, it becomes 1.6, becomes 0.6. So here the voltage becomes 1.753 with this angle. So the angle now between delta GM is 55.2 plus 10 to 5.6. So it becomes 80.8. So this is less than 90 degrees. The system is stable. Still, يعني 80 is in the high side. And if the system operates at 80 degrees, يعني the stability margin is very limited. And again, you are very close to 90. So normal operation, you have the angle around 30 degrees. And I hope you answered this question correctly in the quiz. So the system is stable since delta GM is less than or equal 90 degrees. طيب, for part C, what is part C? We need to find the maximum power or what? Maximum power, right? Part C was asking about the maximum power transfer. So you can get X12, layer transfer reactance, summation of all, and you have X all equal to this. This is now 0.6 for the two lines, and you add them up, and then you can get it Bmax equal to this value, which is 1.215. So in this case, you have more. You can send more power with 1.2. Before system was, or for a single line, system was unstable. But here, you increase the capacity of the transmission capacity by adding another line. So you can send more power here, 1.215. Any question? Right. Let us see this example. In the system shown, the machine is delivering 1 per unit. So this is V equal to 1 per unit. And both the terminal voltage and the infinite bus voltage are 1 per unit. The terminal voltage, this is the terminal voltage here, and this is the infinite bus voltage. These voltage are the magnitude equal to 1 per unit. These are magnitudes. طبعا you can take one of them as your reference and the other one have an angle. Assume that a three-phase to ground fault at point B. At point B, lower midpoint of the line, you have a three-phase fault. It's cleared by opening the circuit breakers at each end of the faulted line. To clear the fault, you open this circuit breaker and you isolate the line. So you have here different configuration. Pre-fault system with two lines. During the fault, we have three-phase fault here, short circuit. as we discussed just in a few minutes before. And to clear the fault, we isolate the line, so you have another configuration. So this line only is here. So maybe we need to, the question here is to find how much the transfer reactance or how much power transfer during pre and post fault, or we can ask for the swing equation, pre fault, during fault, and post fault. So determine the power angle equation, okay, power angle equation for the following cases: for pre-fault, during fault, and after fault in the three configuration. So how much the power angle? So in all cases, E prime, V are constant. So the only variation is x12 to get the power. So the only variation in these cases is x12. In E prime is considered the constant. And now we are talking about very short time. And fault occurs in 6 cycles and 0.1 second. So the excitation of the generator here will not be able to change the induced voltage here, E prime, due to the flux here. The flux has a time constant which is much larger than 0.1 second. وبالتالي usually we assume the E prime constant in this simplified model. So I think how we solved this example at the beginning, how to calculate x12 in all these cases. So this is the impedance diagram, the generator, transformer 0.1, and these two lines, and this is the the infinite bus. Infinite bus معناها انه voltage source, ideal voltage source, as we mentioned earlier. The terminal voltage here is given 1 per unit as a magnitude. How much the angle, we don't know. We assume this as our reference, but this magnitude is equal to 1, but the angle is not known. So what do you think how to get the angle here? How to get the angle? Any idea? Any idea?
Calculates.
So let me ask you, how much power transfer from this point to this point? How much the power transfer? How much the power transfer here? It's given.
One
Abdulaziz Khalid.
per unit.
It is given 1 per unit. Power transfer from E prime to the infinite bus is 1 per unit. وبالتالي برضه power transfer between this point and the same power. So the power transfer between this point and the infinite bus is 1 per unit. So this be equal to the terminal voltage here times the voltage here over the transfer impedance sine the angle difference. So VT, VB over x12, which is 0.1 and 0.2 here, so it becomes 0.3. We sine the angle وليكن alpha مثلا. This angle is alpha, so alpha minus 0. So if this is 1 per unit and this is 1 per unit, you can get the angle of the voltage. Once you get the angle of the voltage, you can get the current. The voltage here is known. The voltage here is known. The impedance in between is known. So you can get the current VT minus VB over the impedance. And once you get the current, you can get the induced voltage here, which is our main target, is to find the E prime. Okay, so this is the case here. In pre-fault, between the terminal voltage and the infinite bus, an impedance equal to 0.3. Here, assume alpha the angle of VT. The angle here is alpha or gamma or whatever. So the electric power transfer is equal to this. So you can get alpha. So this is the alpha of the voltage, terminal voltage. And therefore, you can write the terminal voltage equal to this one with angle 17. And in this case, you can get the current. Current equal to Vt minus V infinity over Jx. And you can calculate E prime equal to Vt plus I times Jxd prime of the generator. So this is the E prime here. And this is the angle delta pre-fault or delta zero. So this is the initial, this is the steady state angle here. The total reactance equal to this at steady state. If we can write the power transfer as equal to the E prime, which is 1.05, times the infinite bus voltage. This is E prime. This is the V bus, infinite bus, over the transfer reactance sine delta. And this delta varies definitely, but at this operating point, the angle delta is equal to 28. But if we have any disturbance, this delta will change, and we are working here, 28 degree. If we have any disturbance, this angle will go up and down, depends on the disturbance. Or you can say, and we have the operating point is here. This is the operating point. This is the specific point. This is delta zero. Okay? But definitely the power angle equation is the equation of this curve. This is just a specific point, but the equation here will be equal to V max sine delta. Okay, so where delta is the machine rotor angle infinite bus, with the infinite bus, no, the under steady state condition, I know the time is over. So this is the during the fault, again, as we mentioned, then we have here short circuit. So you can, here we converted it to admittance rather than impedance, but you can go with the impedance. You can have this impedance here and this impedance here, and you have these are Y connected, you can convert them to delta. This is another approach of having admittance rather than impedance, but it doesn't matter. And it is the same concept, and you can experience this. You can have Y bus matrix, and I think since the time is over, we are not. I don't want to speed up here, but this is Y bus, and you need to eliminate. We will discuss this next class, inshallah. And we will repeat this example again. Do you have any question? Ayub, well?
Doctor, we are using the transient for synchronous generator, but I see that we always use transient even for a steady state analysis. So the transient reactance is different than the steady state, or it's always the same?
That's different, definitely different.
But I see that during fault and without fault, we use the same X prime.
As we discussed earlier, if you still remember, and I would like to go here in order not to mark any thing here. If you still remember, for example, if you still remember here, if we have a fault, this is the fault current and this is the time. You can see at the beginning the fault current is very high and then it goes down, back, and here, and so on. You have some kind of you have such envelope here. And if you still remember, we divide this period to 3 periods: subtransient, transient, and steady state. Okay. So reactance here is called X double prime, XD double prime, and here you have XD prime, and prime for transient, and this is X steady state or synchronous impedance here. Okay. Usually XD prime double prime is lower than XD prime is lower than XS synchronous impedance. So if you look at XD prime and XS, and XS is greater than this, right? So in terms of the transient or during fault or dynamics, which one is more conservative, or let me ask it in a different way. If you assume the reactance of the generator as XD prime, if this is a conservative assumption or not, if you handle the generator with XD prime, if this is a conservative assumption or not.
You mean, Doctor, with the steady state analysis? It's yes.
This is what we are doing here. And no, this is a conservative assumption that you can handle the generator with XD prime. So you are on the safe side. If you have XS, in this case, you have lower voltage or internal voltage of the machine, and the angle will be higher than the angle with XD prime. Is it clear?
Yes, Doctor, clear.
Omar, do you have a question?
Yes, Doctor.
May I ask the one who started recording to stop recording? Don't forget, you can stop recording after 2 or 3 minutes after discussion, but don't forget to stop recording. Okay, go ahead, Omar.
Yes, it is correct to say that the steady state angle is the normal operation of generator.
Okay.
Is it correct to say that at steady state, when generator is operating at steady state, so the angle obtained at that time that is close to 30 degrees? Is it correct to say that that's the normal operation of the generator?
Yes, sir. Usually the angle in normal operation, it is at 30 degrees, somewhere here. Okay, 30 degrees, usually. This is normal case, for the operation. If you start having angles equal to 70 or 80 or 90, you will be in trouble. This is not the normal operation. When you design, in planning stage, when you design the transmission capacity, you need your system to operate at 30 degrees in normal operation. Okay, so you have stability margin here. You cannot design your system to operate at 70 degrees or 80 degrees. You will be in trouble if you have any disturbance. Your system will be unstable. You will lose your system. So this is usually the case, and the angle is around 30 degrees in normal operation. Any other question? Ayub Wael.
Doctor, the transient reactance, we always, take it for a generator, but for transformer, it's not the same. We don't have sub-transient, transient, and steady state. We always take only one reactance.
Yes, in transformer, we don't have any rotating parts. We don't have any rotating parts in transformer. In transformer, we have only one reactance, which is X whatever, X steady state. So X transformer is fixed for sub-transient period, transient period, or steady state period. But when you have a rotating device or rotating machinery, whether generator or motor, in this case, the reactance will change. You have sub-transient, you have transient, and you have steady state reactance if you have rotating machinery. So you are right, in transformer you have only one. We don't have any rotating element or rotating part, so the reactance is the same. Any other question? If there is no question, so you can leave, and we end our class.
Doctor,